Our viewers, I would like to welcome you to my YouTube channel. Today we're going to look at a simple application of the Moivre's theorem. In short, this theorem says that the cosine of an angle theta plus I sine of theta raised to the power of n. This is the same as cos. We drop the power there to multiply the argument, n theta plus I sine. This one will also come down there, n theta. Now, using that argument, we want to do a simple proof where we are multiplying two complex numbers. We want to generalize actually. Given that cos of p theta plus I sine of p theta is our complex number. We multiply this one here by another complex number, which is cos of q theta plus I sine of q theta. Now, this expression here is equivalent to cos of the sum of the two coefficients of theta plus I multiplied by sine P plus Q theta. Now, basically what we want to do here is to prove using the Moivre's theorem that this left-hand side is equal to the right-hand side. So this is our left-hand side. This is the right-hand side. Now, the general layout for a proof is you start on one side, you play around with expressions until you get the other side. So we are going to start with our left-hand side. Now, our left-hand side is equal to cos of p theta plus I sine of p theta. Now, this expression here, according to the Moivre's theorem, it is similar to the right-hand side. Can you see the position occupied by n? Is now occupied by p. And this is being multiplied by cos of q theta plus I sine of q theta, which is also similar to the right-hand side of the Moivre's theorem. Now we are going to apply this theorem here twice, at this part here and the other part, so that we change from this form to the left-hand side form of the Moivre's theorem. Now our first bracket is going to change to cos of theta plus I sine theta, all raised to the power of p. Our n is occupying that position. If we shift it to the other side, it will be our power. I'll do the same thing with that part there. This will change to cos of theta plus I sine of theta, all raised to the power of q. Now let us closely look at this part here. Now at this stage, you will realize that the two brackets, this part as well as the other part, they are equal. It's cos theta plus I sine theta. And we are multiplying the two brackets. Therefore, we are going to use this rule here, laws of indices. X to the power of a by x to the power of b, the result is x to the power of a plus b. You add the powers. As long as these two bases are equal, this product will give us that result. We are having one base and the sum of the powers. Now, since these two brackets are equal, then our result is going to be cos of theta plus I sine of theta, all raised to the power of p plus q. I've added these two powers because these two bases are equal. Now, when you look at Moivre's theorem, this is similar to the left-hand side. Now, according to this theorem, this n here can multiply the angles. But at this stage, our n has been replaced by p plus q. We can still apply the theorem because this p plus q can be dropped and multiply the angles there. So our next line is going to be cos of p plus q, then we multiply by the angle, plus I sine of p plus q multiplied by the angle. So this expression here, if you check properly, it is now equivalent to the right hand side of what we want to prove. Therefore, we can conclude and say this is equal to our right hand side. Now, according to this theorem here, it simply says whatever power is at the top there, it can be dropped and then multiply the angles on the right hand side. Now, let me give you a simple example where we can actually apply this theorem. Right, I will do it here. I hope I will have enough space there. Suppose we are given this simple example, cos of 3 theta plus I sine of 3 theta divided by cos of 4 theta minus I sine of 4 theta. We want to simplify, right? We want to simplify this expression. How do we simplify it using the de Moivre's theorem? Right, starting on the left hand side, yeah, we are going to write this one in this form here, in brackets, to the power of 1. This is the denominator. So since this is going to be treated as our left hand side, we'll rewrite it with this one as a product of the two. So it will be cos of 3 theta plus I sine 3 theta multiplied by cos of 4 theta minus I sine of 4 theta. Now this one will go up. It will be to the power of minus 1. Just to remind you, 1 over x to the n is the same as x to the minus n. This is one of the laws of indices which I actually applied there. This is our denominator, which is being raised to the power of 1. So if it goes up, the power will be negative. Now let us look at the second bracket. We're having a negative power, which is only affecting this part. Now this power here can be dropped according to this theorem here. Instead of our negative 1, it can affect this part and the second part. So this will reduce to cos of 3 theta plus I sine of 3 theta multiplied by cos of minus 4 theta minus I sine of minus 4 theta. There you are. This one is now multiplying this angle, giving us minus 4 theta. It will also multiply that angle, giving us minus 4 theta again. Let me simplify the second bracket a bit. Cos of 3 theta plus I sine of 3 theta, it will give us this product here, which is cos of 4 theta. Remember, cosine is an even function. cos of a negative angle is the same as cosine of a positive angle. But for sine theta, we can pull out the negative sign, which will give us negative and negative, which is positive. So this is going to be plus I sine of 4 theta. Then I close my bracket. This is a very interesting stage now. If you look at this product here, it is similar to what we proved earlier on. This product here is the same as that right hand side. I think we went through the proof. So what are the coefficients of the two brackets? We've got 3 and a 3. We've got a 4 and a 4. So according to this proof here, this will reduce to cos of 3 plus 4 multiplied by theta plus I sine of 3 plus 4 multiplied by theta. The coefficients of theta now are sums of two values, but we can now simplify that. What is 3 plus 4 there? It will give us 7. 3 plus 4 there, it will also give us 7. So this will reduce to cos of 7 theta plus I sine of 7 theta. Now this is a simplified version of that fraction. Remember, we're just applying the Moivre's theorem to simplify a fraction. It is now reduced to these two terms, cos of 7 theta plus I sine theta. I think you enjoyed going through the basics, because these are some of the simple examples where you can actually apply the Moivre's theorem. I'll meet you next time when we do more similar examples. Thank you for listening.